Ultrasound physics is probably the most underutilized and ignored part of both diagnostic and procedural ultrasound. All the applications in ultrasound are underpinned by the physical properties of sound as it interacts with tissue. By understanding these principles, you will be able to get the best picture quality possible. This is so that you can adequately assess the structures of a specific organ system, so that you can then make an adequate interpretation of the images or clips you are trying to collect. It is similar to being in a photo shoot and making adjustments on your camera settings to capture the best possible shot. These building blocks will allow you to choose the correct probe, select the appropriate settings, identify common artifacts, and troubleshoot when you're struggling with poor image quality. We will touch base on the knowledge base on ultrasound physics required for your OSCEs, and touch base on 2D, M-mode, and Color Flow Doppler. Color Flow Doppler has limited applications in diagnostic focus, but we will revisit these principles since they are a foundation for more advanced technologies. These may be an important aspect of the core focus curriculum included in the future. Both pulse and continuous wave Doppler are out of the scope of this lecture. I'll be using the lecture on physics, knobs, and artifacts from showmethefocus.com for reference. I need to warn you that I'll be repeating some terms constantly throughout this lecture, and it is to help you consolidate this information. Let's go. Ultrasound physics is broken into 3 major chapters so that the information provided is bite-sized and easy to follow. This is part 1 of the lecture series where we focus on the basic building blocks of ultrasound, ultrasound modes, probe selection, and tissue interactions, as well as knobs and artifacts, are part 2 and 3 of this lecture series. The full lecture is also available if you would like to watch this 1-hour lecture in one go. Our main objective behind this lecture is to recognize fundamental ultrasound physics so that the highest possible image quality and scene clips can be used for image acquisition by being able to recognize the basic components of sound waves and those of the ultrasound probe, recognize appropriate probe selection for a given application, recognize ultrasound machine controls or knobs, recognize ultrasound properties that lead to optimization of image acquisition, including selecting appropriate depth, sector width, frequency, focus, gain, harmonics, dynamic range, and acoustic power. Recognize features of spatial and temporal resolution as well as the interactions of ultrasound with tissue, identify commonly encountered artifacts, and strategies that can be used to eliminate them depending on the specific focus application. Recognize when the examination is beyond the technical or interpretive capability of the focus exam on a particular application. This goal is further explored in the specific organ system. Recognize the biological effects and safety of focus. Technology explored includes 2 dimensions, M-mode, and Color Flow Doppler. Color Flow Doppler is out of the scope of most focus exams. It is explored here as part of the OSCEs. Spectral Doppler is out of the scope of the focus exams and is not explored here. To start, a common theme is choosing the correct probe. We have 3 ultrasound probes in front of us. These have different frequencies for different applications. Some of these are small and square, others are thick and bulky. There's a reason behind these designs. But before we can start classifying what they can be used for, their advantages and disadvantages, we need to get some understanding on the basic physical properties of ultrasound. Sound waves. Sound waves are mechanical vibrations that alternate between expansion and compression of any physical medium through which the sound wave travels, with the exception of a vacuum. It is an oscillation of pressure transmitted through these mediums. These waves travel in a straight line on its longitudinal axis, and the medium's molecules move back and forth. A particle that is in resting condition is first disturbed, causing it to vibrate, which then exerts this force on the adjacent particle. That first particle then returns to its original position. The particles of the medium do not move forward themselves, but the vibrations are carried forward. When particles move forward, it compresses the air in front of it, creating a region of high pressure known as compression. When the vibrating object moves backwards, this creates a region of low pressure called rarefaction. The sound wave is graphically represented as a sinusoid wave, with areas of compression representing the upper part of the waveform and rarefactions being represented by the lower part of the curve, with low pressure regions. The maximum compression and density is located at the peak of the waveform, while the lowest pressure and density region is located at the trough of the waveform. Sound waves have 4 physical properties. Amplitude. This is the distance of maximum displacement from the resting position and represents how loud the sound is. Increasing the amplitude increases the acoustic pressure or the pressure generated by the crystals that emit sound. It allows the ultrasound machine to hear a louder return sound signal. Wavelength. The wavelength is the length of one wave cycle from peak to peak, which includes one rarefraction and one compression. Frequency. The frequency of a sound wave is the number of cycles or waves per second. This is not the speed of sound in a medium. This is a value given in hertz and represents the number of waves that fit in a second. A small wavelength will yield a higher frequency. The human hearing range is between 20 Hz to 20 kHz. Ultrasound is anything higher than this range. The typical range of medical ultrasound probes is between 1 to 20 MHz. The period is the amount of time it takes for a single cycle to occur, and it's the inverse of frequency as it is time per cycle. Period has unit measures in time, while wavelength is measured in distance. A period is determined by the sound source, not the medium through which the ultrasound signal travels. Period and frequency are inversely related. A high frequency wave has a short period. Propagation velocity. This is the velocity that a sound wave travels in a medium. Propagation velocity is determined by the medium through which the ultrasound wave travels. Sound waves of the same frequency travel at different propagation velocities in different mediums. The propagation velocity of average human tissue is 1,540 meters per second. That of air is 343 meters per second, and that of bone is much higher at 4,080 meters per second. Since velocity is distance over time, the propagation velocity is a product of wavelength, which is a unit in distance, and frequency, which is cycles per time. As the sound wave travels from one medium to another medium, the propagation velocity changes. This is important since the ultrasound machine assumes that all tissues have the same velocities and the reason we appreciate artifacts, as we shall later explain. Transducers. The transducer is one of the most critical components of any diagnostic ultrasound system. There are many types of transducers, and it is important to select the one appropriate for the planned application. Diagnostic transducers act as both transmitter and receiver of ultrasound. Let us look at a transection of a typical transducer and its components. The primary component of the transducer is the piezoelectric ceramic element, composed of different materials including lead zirconate titanate. The crystal is the mechanism that allows transmission and reception of ultrasound waves. In this review, we'll be using the term crystal to refer to its piezoelectric element. It transmits ultrasound waves after being stimulated by an alternating electrical current. These pulse signals are reflected back to the piezoelectric crystal, which then generates an electrical signal that is then processed and displayed. Notice that the crystal does not emit a single wave, but a pulse composed of a varying number of cycles. The piezoelectric element is housed in a transducer, which also contains a damping material, an acoustic lens, and a matching layer. When stimulated, the crystal vibrates in all directions, with the majority coming from the front and back. This is inconvenient since we only need it from the front or the patient's side. The backing material or damping block tries to eliminate vibrations on the back of the crystal and controls the length of vibrations from the front face. That is, it controls the number of cycles emitted in a single pulse. The matching layer reduces the acoustic impedance so that ultrasound waves can penetrate body tissue and allows the returning echoes to be returned to the crystal for the same reason. Think of acoustic impedance as the resistance to flow of sound waves through tissues. This is the reason you always want to use gel in front of a probe so that acoustic impedance lowers enough to let the waves in and out of tissue. The frequency of the transmitted ultrasound waves depends upon the type of crystal and its thickness. For maximal efficiency, the crystal should be operating at its natural frequency and occurs when the thickness of the crystal corresponds to half its wavelength. Another way to think about this is that the wavelength is equal to twice the thickness of the crystal. So, crystal thickness is proportional to its wavelength and implies that a thicker crystal has a higher wavelength, which will penetrate into tissues more than a thinner crystal. On the contrary, a thinner piezoelectric crystal produces higher frequencies with a lower wavelength. To help you remember, the thickness of the crystal should be proportional to the distance you are trying to scan. Bigger crystal, bigger waves, more distance. The sequence is as follows. The ultrasound probe generates a pulse. This consists of 2 or 3 cycles of the same frequency that travel along the path called a scanned line. The crystal is not stimulated during the next few milliseconds, and it is during this time that the waves that are reflected back to the transducer are received by the crystal and an electrical current is generated back to the machine. The received signal can then be processed and displayed. The amplitude of the returning signals are represented by its brightness or echogenicity. Strong reflections produce bright or hyperechoic images, such as those seen with bone. For reflections that are not as intense, produce a grayscale of reflected images. At the other end of the spectrum, we have no reflection at all that produces anechoic images, such as that produced by blood vessels. Resolution. The quality of the image displayed must be such that we want to be able to identify all the structures that lie in the path of the ultrasound beam and be able to discriminate between these structures in space and in time. Resolution is the ability to distinguish objects from each other. This is determined mainly by the type of transducer we choose. It comes in two varieties. We have spatial resolution, which is the ability to determine the location of objects that lie next to each other. And then we have temporal resolution, which is the ability to determine the location of an object with regards to time. Spatial resolution is further divided into axial and lateral resolution. We will review these concepts further along in this lecture, so stay with me. Axial resolution is the ability to distinguish two separate reflective objects that are longitudinally adjacent or slightly deeper than the other along the ultrasound beam. Imagine the following example. There are three pairs of reflective objects, and each other is right next to each other, but slightly deeper than the other. These three pairs of objects are located at different depths embedded in tissue: shallow, deep, and very deep. An ultrasound beam will go through them, and they reflect these pulses back. You're given to choose between a low and a high frequency probe. If you choose a higher frequency probe, you'll be able to see three pairs of objects. If you had chosen a lower frequency probe, you may see on the screen that there is one object instead of a pair located at each depth. The actual resolution doesn't change with depth. The actual resolution in this last example is, of course, worse. Pulse length. The major determinant for axial resolution is pulse length. The pulse length, or duration, is the distance in time each pulse travels. This length of time has an impact on the resolution of the image. A shorter pulse duration provides better axial resolution than a longer pulse duration. In fact, axial resolution is equal to 1/2 of the pulse length. The smaller the number, the better the axial resolution. This is why a higher frequency probe will allow you to get better axial resolution. Think of the pulse being small enough to fit between two objects along the path of the wave. A physical property related to pulse length is the pulse repetition period. The pulse repetition period is the time from the start of one pulse to the start of the next pulse. It is thus the pulse length plus some listening time. The length of a pulse can be changed by changing frequencies, but the pulse repetition period is mainly determined by the listening time. The listening time is the time that the transducer is able to receive reflected signals from the transmitted beam. Once the depth of an ultrasound scan is increased, a longer listening time is required to be able to receive reflected signals. Therefore, the depth of the scan mainly determines the pulse repetition period. Pulse repetition frequency is inversely related to pulse repetition period. It is the number of pulses transmitted per second given in hertz. A deeper scan requires a slower pulse repetition frequency to allow the deeper reflected signals to be received during this listening time. This property will come into play when dealing with temporal resolution. The important feature here is the pulse length and pulse repetition period are not the same. Lateral resolution. Lateral resolution is the ability to distinguish two separate reflected objects that are adjacent and perpendicular to the ultrasound beam. This type of spatial resolution is typically worse than axial resolution. Regardless of the probe used, the profile of the beam generated changes with regards to its distance from the transducer. To start, the width of the beam is approximately the same size as the width of the transducer. The beam then converges to its narrowest width, known as the focal point, at a perpendicular distance that is half of the width of the transducer, and altogether it forms the zone called the near zone length, or the Fresnel zone. Once we are past this near zone, we enter the far zone, also known as the Fraunhofer zone, where the ultrasound beam diverges. At twice the near zone, the beam now has the same dimensions as the width of the transducer. Lateral resolution is high when the ultrasound beam is narrow, we would want a long near zone since this provides the best lateral resolution. The near zone is proportional to the square of the diameter of the probe and inversely related to wavelength. Lateral resolution is best within this near zone, and so we must choose a probe that allows us to have the longest near zone. A broad, high frequency probe fits the bill. Imagine a similar example as we described above. Instead of the pairs of objects being slightly deeper, now we have them lie beside one another. You are given to choose between a narrow and a broad probe, with both having the same frequencies. The broad probe will cast a longer near zone than the narrow one. If the pair of objects are in the far zone, then we would see one instead of two objects. For this reason, we would want to choose a broad probe for better lateral resolution. Focusing. So far, we have seen what happens when the probe is casting an unfocused beam. That is to say, the beam has the same size as the width of the probe, narrows at half its width and distance, then the ultrasound beam diverges. We can in fact force the piezoelectric elements to operate at different times or distances to narrow the ultrasound beam, which creates a focal region within the near zone. We see this in action in these two examples, with focusing being turned on at different distances. Notice the better lateral resolution of this second example. This is a focus beam, and it shortens the distance of the narrowest point of the beam cast by the transducer. This allows for an optimal lateral resolution at what is known as the focal length by reducing the near zone length. At the far side of the focal region, the beam diverges and the lateral resolution worsens. The width of the focused beam is proportional to wavelength and inversely to the width of the probe. Again, we would want a narrow focused beam for a better lateral resolution, and to do so, we want a broad probe with high frequency. The ultrasound beam is proportional to the width of the probe and inversely proportional to wavelength. Focusing mainly affects lateral resolution. I recap on what we have seen so far on spatial resolution. A thinner broad probe has higher frequency signal since wavelength is proportional to the piezoelectric element's thickness. The probe has smaller and thus better axial resolution since the pulse length is smaller. Axial resolution is half the spatial pulse length, and so we want a pulse that is small enough to fit between objects that are deeper to each other. This high frequency probe would also have a better lateral resolution since the near zone is long, since this is proportional to the square of the width of the crystal and inversely proportional to its wavelength. For optimal lateral resolution, we would want a narrow focus beam width, and this implies a high frequency probe with a large diameter of piezoelectric elements. By selecting a focus depth that includes our target area, we'll be getting the best lateral resolution that probe has to offer. Temporal resolution. Temporal resolution is the ability of the ultrasound system to distinguish between events of rapidly moving structures that are separated in time. When we're using the brightness or B mode in ultrasound, all the piezoelectric elements are simultaneously scanning a plane by emitting repeated pulses. These pulses create their corresponding scan line, and once they return to the probe, they are then represented in the ultrasound display as a single frame. What we see on the ultrasound display is a sequence of these generated frames. Temporal resolution is driven by the frame rate, which is the time it takes to go from one frame to the next. In this sense, we would want a high frame rate. Think of a movie with a low versus a high frame rate. The high frame rate appears more realistic because it offers a smoother transition and one in which you can tell where objects are at any point in time. The frame rate will likely be displayed in your ultrasound system, as is this case. Factors that improve your frame rate include the following: reducing the target's depth. Pulses need to travel less distance, and it is faster for the machine to process a frame, so we want a high pulse repetition frequency. Remember that the listening time increases with depth. The less listening time, the higher the frame rate. Next, reducing the number of scan lines. Temporal resolution can also be improved by picking a reduced number of scan lines per frame, since there are less scan lines to process. Eliminating focal points. Reducing the number of focal points reduces the need to duplicate the scan lines. In summary, when using 2D, to obtain the best temporal resolution, we 1. Choose the shallowest depth possible to visualize our target. Picture obtaining the parasternal short axis view. In this view, we want to see all the walls of the left ventricle, and so the far field should not be deeper than this structure. Choosing a deeper distance will make it difficult to visualize shallow objects and worsen temporal resolution. So we want it to be a shallow depth. Next, we need to narrow the sector, which is the area of the ultrasound display. If we want to have a better temporal resolution, we want a smaller piece of the display pie. And then finally, we can remove focusing so that the ultrasound machine does not have to duplicate scan lines. Remember, spatial pulse length is actual resolution and we want it small. Pulse repetition frequency is temporal resolution and we want it high. Lateral resolution has to do with the width of the beam.